Hello everyone, welcome to the lecture series on IC applications. Myself Siva Ramakrishna, Assistant Professor in ECE. In this lecture, we are going to continue the discussion on data converters. So let us quickly look at the things we have discussed so far. We have seen the need for data conversion and what are different types of data converters, and we have provided a brief introduction on digital to analog converters and analog to digital converters, and the discussion is presented with respect to an example called a plant having a set of tools, a set of elements. So that is, the signal is generated from a plant and it requires to process to improve the quality of the signal. So where we have explained the need for data converters, both digital to analog as well as analog to digital converters. So with respect to starting from a plant to a processor, so this processor will process the data that is going to be a digital, and then as an end user, we humans cannot understand the digital data which is expressed in binary ones and zeros. So we need to convert the data back to analog form. So there we are going to use digital to analog converters. So this is the overall for block diagram that will demonstrate the need for analog to digital converters as well as digital to analog converters. We explained this with respect to a transmitter and receiver in any communication system, right? And we have seen the need for data conversions in the context of several applications, right? Also we have discussed, so these are the things we have seen in the last few classes, right? And we said the most important data, so which has abundant applications in nature, are going to be two. So what are they? The data can be digital form or it can be analog form, and in the application one needs to convert this analog data to digital, also needs to convert digital data to analog. According to this, we have two types of converters. So we said the converters are going to be analog to digital converter, and the second one is digital to analog converter. Also we have seen a brief introduction regarding digital to analog converters. We said the digital to analog converter is in nothing but an electronic circuit or an interface which will accept input as a binary data. That is, the interface will accept binary data as input and will produce analog data as output. So both digital to analog converter as well as analog to digital converters are going to be some kind of electronic circuits. So in this we are going to realize these converters by using operational amplifiers, right? And we said the applications. So it is just a journey of data converters. We started discussion on what is the need, what are the key components, and then we have highlighted the significance of each converter, where we are going to use them are nothing but digital to analog converter applications. We said digital audios, digital video, and in many communication equipments and PC, definitely all our computers operated with digital data. They are not going to work with analog data. So they need to convert the incoming digital data to the incoming analog data to digital data to complete the process, right? So these are a few examples we have highlighted, right? And similarly we have demonstrated, so what is meant by analog to digital converters? What is analog to digital converter? Again, this is going to be an interface or an electronic circuit that converts analog data to digital, right? Most probably this circuit will present in the transmitter path, right? And what are the common elements that do appear in analog to digital converter? There will be a sampling technique, there will be a quantizer, and finally the quantized levels are going to be assigned by binary 0 or 1. So we said it can be, finally the data is going to be a binary data which is expressed in terms of ones and zeros, right? And coming to the applications, in what are all the applications, where do we come across these interface or circuits? Are nothing but, so digital workstations, in the case of digital signal processing, so where we need microcontroller or signal processing applications, one needs to work with these converters. Before processing the data to the next level, we need to convert this data, right? And then in the next class, we have seen, we started the discussion on digital to analog converters. So what are various types of digital to analog converters? So this is the functional block diagram of what we can say, a basic digital to analog converter. As we said, this takes this digital data as input, will have MSB and LSB, and then produce the output is nothing but analog voltage, right? Nothing but some electrical voltage is the output for corresponding binary sequence. So the data can be 2-bit, 3-bit, 4-bit data. Depending on that, will produce the corresponding output voltage. And we said the types of converters are going to be basically 3 types. What are they? They are going to be weighted resistor DAC, R2R ladder DAC, and then the third one is going to be the inverted R2R ladder DAC. We have seen the demonstration on weighted resistor DAC. So we discussed the operation and we have derived the expression for output voltage by performing some nodal analysis. We are able to express this output voltage in terms of the reference voltage and binary, that is binary data, where B0, B1 or B2 are going to be the binary data or digital data. So these are going to be the digital data, right? This is an example for 3-bit operation, right? And later we have generalized this expression for digital to analog converter. So what is the technique? Weighted resistor type. So this is the generalized expression. This is the generalized expression for weighted resistor type digital to analog converter. So where VR represents the reference voltage. So where VR represents the reference voltage, and these are the binary data or nothing but digital input. So these are going to be the digital input, right? So this we have seen, and then we find the relation between the digital data as well as analog output, digital input and analog output. It seems to be like a staircase response. That is the relation between digital input and analog output. And then we have highlighted the drawbacks of weighted resistor DAC. So we said it is going to be a weighted resistor DAC. What are the drawbacks of it? There are few number of drawbacks. So the first one is going to be the difference between the resistor values for LSB and MSB is very huge, right? And then we need more number of resistors to build this weighted resistor network, and these resistors are going to be of large values. So it is not a 2 resistors or 3 resistors or 4. The resistors are going to be huge, and the values of these resistors are going to vary abnormally. That is, the difference between any 2 resistors is quite large. And we said the resistance of the binary data usually expressed in the form of a sequence. So we are going to have LSB and MSB. The resistance value of this LSB is quite high than MSB resistance, and which is very low. The resistance value of MSB is very small compared to any other resistors in the weighted resistor network, whereas the resistance value of LSB is very huge compared to any other resistors in the weighted resistor network. And it is very difficult to design such a number of resistors with high precision and accuracy. So these are the major drawbacks we have seen. Right? In this lecture, we will come up with a new technique which will overcome these drawbacks, which will overcome the drawbacks of weighted resistor DAC, right? And the technique is going to be R2R ladder DAC. So if you observe the circuit, once again we are going to design it using an operational amplifier. Let us say this is our IC 741, and as usual we are going to have inverting as well as non-inverting terminals, and we are going to connect a network. This time the network is going to build by using only two types of resistors. Are going to be R. The resistance value can be R, it can be 2R. Unlike the previous design where the value of the resistance varies continuously and the difference of the two resistors is again very large. Here the situation is quite different. We are going to use only two types of resistors, and this network is connected to inverting terminal of the operational amplifier. If we observe the circuit, see here, this is once again for a 3-bit operation. This is going to operate with a 3-bit operation. That is, we have B0, B1 and B2. So where B0 is going to be LSB and B2 is going to be MSB. So this is a 3-bit DAC. Nothing but R2R DAC. The name R2R represents, in any network, the values of the resistors are going to be R and 2R, right? Irrespective of the binary data, whether it is LSB or MSB, right? These are the networks, and once again we are going to use switches. These switches are going to be digital. These are going to be the digital switches, and these switches are going to connect between ground or the reference voltage, right? This portion remains same or similar to that of the previous design. So when they are going to connect to the ground, if the incoming binary data is 0, then the switch will be connected to ground. If the incoming binary data is 1, then the switch will be connected to the reference voltage. Here we are using a negative reference voltage, that is minus VR, right? And the output is obtained across the output terminals through a feedback resistance. So this is a feedback resistance having a value of 2R. This is a feedback resistance with a value of 2R, right? So this is an illustration for 3-bit operation. Now let us analyze this circuit, right? Let us simplify. Analysis means we need to derive the expression for output voltage V0. What is the expression for output voltage? As we said, this output voltage depends on the values of the resistors present in the network, which is connected to the inverting terminal, right? So let us consider two nodes as A and B, and this is for 2-bit operation. Let us discuss a 2-bit R2R ladder DAC. The two binary bits are represented by, let us say this is going to be the B0 and this is going to be the B1, right? are the two binary data. So now let us analyze this network. Let us analyze the network. So we are going to consider this part for the analysis, and then we are going to determine the voltage across this node. Let us say this is applied to the inverting terminal of the op amp, and the voltage is represented by VA. VA is the voltage applied to the inverting terminal of the op amp. So now let us consider this portion of the network and analyze it. So this is what we are going to have, right? Once we consider the network connected to the inverting terminal, so if we observe, the resistors R and 2R seems to be in parallel. So the equivalent resistance is going to be, how can we find this equivalent resistance? It can be determined R effective. The equivalent resistance is obtained as R equivalent equals to 1 by 2R plus 1 by R. Since these two resistors are in parallel, right? So if we simplify this, what we are going to have? So it will be 1 plus, so which means the simplified analysis, if we simplify this, we are going to have 2 by 3R as an equivalent resistance out of these two resistors, right? So it is very simplified, this one, right? And this is represented as the resistance across the node A, right? And so here let us consider the binary data. So what is my binary data? So B0 is going to 1, and so let us consider the data. So what are the possible incoming data for a 2-bit data? For a 2-bit digital data, it can be 00, 01, 10 and 11. These are the possible incoming data sequence for a 2-bit operation. So now let us say B0 is going to be 1 and B1 is going to be 0. So 0 means it is connected to the ground. So as we said, if the incoming data is binary 0, then the corresponding digital switch is connected to the ground. And we said that is B0 and B1. So B1 as 0 and B0 be, let us say B0 be 1, right? Now since B0 is 1, the switch is going to connect with the reference voltage, which is minus VR. Now this is our equivalent circuit for analysis, or the simplified network for the analysis. So we are going to consider the voltages across this node A and node B. So now let us proceed further. So what we are going to have? So what is considering the node A alone? So what are the possible currents across this node we can have? So one is going to be VA by 2/3 R plus VA minus VB by R, and it is going to connect to the ground, so it is 0, right? Now if we simplify this, so what we are going to have? So it will be 3 VA by 2R plus VA minus VB by R, which is equal to 0, right? Now if we take LCM as 2R, so what is our expression now? Here we are going to have 3 VA plus 2 VA minus 2 VB. So this is what we are going to have. It is 3 VA plus 2 VA minus 2 VB by 2R equal to 0. So which leads to 3 VA plus 2 VA is going to be the 5 VA, and we are going to have minus 2 VB. So the expression will be like this. After performing the cross multiplication, we are going to have 5 VA minus 2 VB is equals to 0. Therefore, VA, that is, we can write it as 5 VA equals to 2 VB, and we can define VB from this equation. So what is VB now? VB can be written as 5 VA by 2. So this is what we are going to obtain by simplifying the network and considering the signals at node A. Right? We have VB equals to 5 VA by 2. Now let us consider node B this time. Let us consider the node B. So what we are going to have? So by considering node B, we will have 3 terms. We are going to have 3 terms. They are going to be VB by 2R, this one, and then it is going to be VB minus of minus VR by 2R by considering this path. So this is, and considering this third one, it is going to be VB minus VA by R, and it is going to be 0, right? So now if we simplify this, once again taking LCM as 2R as LCM, we are going to have, so what are the terms we will have? VB plus, so it is going to be VB plus VR. So this minus minus becomes a plus. So we are going to have VB plus VR plus 2 VB minus 2 VA. So total how many terms are there for VB? So there will be 1, 2 and then 4. So it is going to be 4 VB plus VR. 4 VB plus VR minus 2 VA by 2R is equals to 0. This is what we have. And now once again, if we perform this cross multiplication, that means the denominator is getting multiplied with 0. So the expression is going to become 4 VB plus VR minus 2 VA equal to 0. So the objective of this analysis is to determine the voltage VA, because later VA is applied as input to the inverting terminal of operational amplifier. So considering this second equation, let us say this as the second one and the previous one as the first one, where we define VB. So VB as 5 VA by 2. So we can write this VA as, so what is VA now? From this expression, we can define VA equals to that is VA is equals to, we are going to have 4 VB, that is we have 2 VA of course, 2 VA is equals to 4 VB plus VR. So that means VA is equals to, so we are going to have 2 VB, so that is 4 VB plus VR divided by 2. So what we are going to have, VA is equals to 2 VB plus VR by 2. So this is what we have by considering the signals across the node B, right? And we already defined VB. What is VB? VB equals to 5 VA by 2. So we have VB as 5 VA by 2. Let us substitute this expression in this third one. Let us say this as the equation number 3. So we have VA equals to 2 VB plus VR by 2. So let us substitute it. So we have, so the expression is going to be VA is equals to 2 VB plus VR by 2. And we know the value of VB, that is 2 into 5 VA by 2 plus VR by 2. So both these two will cancel each other, and we are looking for the expression VA. So what is the result now? Let us bring this to this side. We are going to have 5VA minus VA plus VR by 2 is equals to 0. So this will be 4VA plus VR by 2 equals to 0, and we need to determine VA. So what is VA now? VA is going to become minus. So we are going to move this term to the other side. It will become minus VR by 2. And here we have a coefficient as 4. So again, bringing this 4 to other side, we can define VA as minus VR by 8. So what is the expression for VA? That is the voltage applied to the inverting terminal of operational amplifier. This is for 2-bit data. For a given 2-bit data, and considering 1-0 combination. Considering 1-0 combination where B0 is 1 and B1 is 0. So we have VA equals to minus VR by 8. So this is what the network we have analyzed, and here we have the signal that is going to be VA, where VA is equals to, so that is VA equals to minus VR by 8, right? So this is the input to the inverting amplifier. So let us redraw this quickly. We have an inverting op amp output as V0. So this inverting terminal holds a value of VA. Of course, this non-inverting terminal is connected to the ground, and here will be the output through the feedback resistance 2R. Right, with this we can define V0. Now what is V0? Since it is an inverting amplifier, V0 can be written as minus 2R by R into VA. So what is VA now? VA equals to minus 2R by R, and VA as minus VR by 8. So this is what we determine for VA, minus VR by 8. Right, now if we simplify this, we are going to have the output voltage. The output voltage is going to become VR by 4 for the incoming binary data 1-0. Right, so this is the expression for output voltage, and we can perform the similar analysis. We can perform the similar analysis for other bit sequence or other bit configuration. So that is, we said LSB is 1 and MSB is 1. So LSB is 1 and MSB is 0. So this is the expression we have determined. The output voltage for this expression is determined, and which is going to be VR by 4. And if we generalize it, if we generalize this analysis, the output can be written as like this. The output voltage V0 equals to, for a bit combination of 0, 0, the output voltage can be expressed as, so this is what the analog output voltage. So for incoming data 0, that means both LSB and MSB are 0, which means both the digital switches are going to connect to the ground. No switch will be connected to the reference voltage. So here the corresponding voltage will be expressed as 0 into VR by 4 if we generalize it. And now we have seen for the binary data 0, 1, where LSB is 1, MSB is 1, MSB is 0, for LSB is 0 and MSB is 0. So what is the value we have? We can represent this as 1 into VR by 4. This is what we obtained, right? This is what we obtained here. And for the binary data 1 0, the value can be expressed as 0 into VR by 2 into VR by 4. This can be written as 2 into VR by 4. And the third one is going to be 1 1. Third data sequence will be 1 1. So here the data can be expressed as 3 into VR by 4. So this is a generalized representation of the corresponding voltages for different data sequence, right? So what we are going to have for incoming data 0 0, the output voltage is going to be, the output voltage will be V0 is 0, and for the 0 1 the output voltage is VR by 4. For 1 0 the output voltage is 2 VR by 4, and for the third last sequence 1 1 the output data is going to be 3 VR by 4. So this is how one can generalize and perform the analysis of this ladder DAC, right? Here if we analyze if we determine the output voltage for any data sequence, that can be generalized for other data sequence. So this is an illustration for 2-bit data, right? Similarly we can analyze for 3-bit data. If we have a 3-bit data, we are going to have another R2R network. For 2-bit data, we have a pair of, we have two number of R2R ladder networks. For 3 number of data, for 3-bit data conversion, we are going to have 3 number of R2R, and similarly we can proceed further, right? So since it is a 2-bit data, this is R2R and this is R2R 1 and 2. If we have a 3, we are going to have another such combination of R and 2R. Similarly, if we have a 8-bit data operation, for 8-bit data operation it is going to be 8 numbers of combinations of R2R. There will be 8 number of R2R ladders, right? So now let us discuss the advantages and disadvantages of this R2R ladder network. These merits and demerits are explained with respect to the construction of the network, right? So one thing is common in the case of digital to analog converters. We need to build a network. We need to build a network with the help of a number of resistors or a group of resistors. Now the challenge is how you are going to build that network. So whether it is a simple or complex. If we recollect the previous technique, weighted R2R, weighted resistor DAC, that network construction is quite complex, right? Whereas here it is a simple in construction, because I need only 2 types of resistors. What are they? We are going to use R, and another resistance value is going to be 2R. There is no third type of resistor here. We have only R, and the second one is going to be the 2R. So that's why comparative to the previous network, comparative to the previous weighted resistor network, this is very simple in design. And so later we are going to discuss the specifications of these data converters, of which one important thing is speed of conversion. What is meant by the speed of conversion? We have an input. So this is input coming to the DAC, and what is the time required to convert that into, so this is DAC, this is my input digital data, and this is the output. So what is the time required? What is the time required to convert this input data to output? Conversion of data from digital to analog. So compared to the previous one, What is the previous one? Weighted resistor DAC. So it has a fairly speed or fast. So that's why we said it provides a fast conversion of data, that is from digital to analog. So these are the merits or advantages of R2R ladder DAC. And coming to the drawbacks, so this type once again requires large ranges of resistors with necessary high precision for low resistors. So this number called high is highlighted because of the number of bits, right? As the number of bits of operation increases, we are going to have more and more number of pairs of R and 2R with high precision, right? And requires low switch resistance in transistors. That means a switch can be of we said it is a digital switch. A transistor can be used as a switch, or effect can be used as a switch, right? Whatever the element that we use as a switch, that is the element is going to perform as a switch, it should possess a low resistance, right? So this is the requires low switch resistance, or otherwise if the resistance of the switch used in the design is fairly high, the impact of this resistance also do considered in the analysis, and it will affect the performance of this DAC, right? And definitely it is going to be expensive, hence resolution is limited to 8-bit size, right? So these are reasonable drawbacks compared to weighted resistor DAC, right? And this design with high resolution, later we will define while discussing the specifications of data converters. We will define another term called resolution. So by this time we come across two specifications. One is resolution and conversion time. What is the time required to convert the data, and what is the resolution? Resolution will be discussed in the other class. That is where we are going to focus on specifications of this data converters, right? These are the drawbacks of this R2R ladder DAC, also the advantages. So when compared to the weighted resistor, it is fairly good. So that comment we can use. And the other common drawback in both weighted resistor as well as R2R DAC is current variations. That means the current through the resistors will vary abnormally, which means the current through the resistors is not uniform. There will be different amounts of currents will pass through the resistors, right? This is a common drawback and as a challenging one. This do exist in both weighted resistor DAC as well as this R2R ladder DAC, right? And in the next class we will try to focus on how to overcome this drawback of current. That means how to regulate or how to control these variations of currents. So we want the currents through the resistors should be same and uniform, right? If the variations in the currents increases abnormally, there will be a possibility of high amount of power dissipation, right? This power dissipation later affect the performance of the converter because of excessive heat, right? So what is the common drawback? The currents through the network are not uniform because we have different resistors. There will be non-uniformity. That means the current through the network is not same through all the resistors. This will leads to power dissipation, and further this is a high amount of power dissipation, and this causes excess heat. This causes excess heat in the circuit. So that will affect the performance. So this may later produce a wrong output across the output terminals, right? So this is a challenging one. In the next lecture, we are going to discuss inverted R2R DAC. So there we will try to overcome this drawback. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.